This is the second video for section 3.1 where we'll talk about the second derivative test. So the second derivative test gives us another way to determine whether or not critical points are maxes or mins. So let's think about critical points of the type f prime of c equals 0. So if that's the case, then f has a horizontal tangent line at x equals c. So let's see some examples. So here's a nice example of a function that has a horizontal tangent line at c, and let's notice something about it. First of all, it's concave up at c, and c is a local min. Okay? Now here's another nice function that has a horizontal tangent line at c. Let's notice something about it. It is concave down at c, and c is a local maximum. And here's one final picture. This is some translated version of maybe x cubed. It has a horizontal tangent line at c, but notice that the concavity changes. So it goes from concave down to concave up as we move from left to right. And c is neither a max nor a min. So these pictures motivate the second derivative test. And that is the following. Let's suppose that I have a critical point of f of x such that f prime of p equals 0 and f double prime of p does not equal 0. Then I can use the second derivative to determine whether p is a local max or a local min. In particular, f has a local max at p if and only if the second derivative at p is less than 0. So if and only if f is concave down at p. And f has a local min at p if and only if the second derivative of f at p is greater than 0, or if and only if f is concave up at p. So that's great. Notice something, another word of caution here. F double prime of p equals 0 gives us no information. That case is specifically disallowed in the second derivative test. And here's why. If f double prime of p is equal to 0, anything can happen, and I'll show you three different pictures. So the first picture is f of x equals x to the fourth. The second picture is f of x equals negative x to the fourth. The third picture is f of x equals x cubed. Now, in the first picture, x to the fourth, I have a local min. In the second picture, x equals negative x to the fourth. At 0, I have a local max. And in the third picture, f equals x cubed, I have neither a max nor a min at 0. However, all are such that they have horizontal tangent lines at the origin, so f prime of 0 equals 0, but they also have the property that you should check that f double prime of 0 equals 0. And three different behaviors are occurring. So if even if the first derivative at 0 is 0, even if I have a horizontal tangent line, if the second derivative is 0, I can make no conclusions. So the second derivative test works except in this case. So let's see how. This is your example from the last video. F of x equals 1/3 x cubed minus x squared minus 3x plus 1. And what we know from the first video is that the critical points are x equals 3 and x equals negative 1. So I'd like you to use the second derivative test to determine if they are maxima or minima. We already know the answer, but let's just see that the second derivative test gives us the same results. So I take the first derivative, x squared minus 2x minus 3, differentiate that to get the second derivative, which is 2x minus 2. So f double prime of 3, so how am I going to use the second derivative test? Here, all I have to do is plug in my critical points into the second derivative. So f double prime of 3 is 2 times 3 minus 2, which is greater than 0. So the second derivative test tells me that my function's concave up, so that means 3 is a local minimum. And if I evaluate f double prime at negative 1, I get 2 times negative 1 minus 2, which is less than 0. So the second derivative test tells me my function is concave down, which means negative 1 is a local maximum. So using the second derivative test is really easy when it works. But let's say that I asked you an additional question. Where is f concave up or where is it concave down? We might call these intervals of concavity. So for this, it's useful to have a definition. A definition is the following. An inflection point is a point where the concavity of our function changes. So that's what we'll call an inflection point. And inflection points can occur when either the second derivative equals 0 or when the second derivative does not exist. So if we think about it, what does it mean for the concavity to change? It means the sign of the second derivative goes from positive to negative or vice versa. That can only happen if either we're crossing the x-axis, so if f double prime equals 0, or if we have some strange discontinuity and f double prime does not exist. So let's find our inflection points of f of x, our same function, 1/3 x cubed minus x squared minus 3x plus 1. So the first thing we need to do is we need to find what possible inflection points could be. So we take the second derivative, it's 2x minus 2. It's a perfectly continuous function, so the derivative exists everywhere. So the only possible inflection points are going to be when this equals 0, which if we solve for x, we get x equals 1. That is a possible inflection point. We must go further. We must show that the concavity changes at x equals 1 to conclude that it is indeed an inflection point. So I do another number line, and I really encourage you to label your number line. So this is the sign of the second derivative, is what we're looking at in this number line. So again, the only possible place that f double prime could change sign is at 1. So it is enough to look at any value to the right of 1, like 3. F double prime of 3 is 2 times 3 minus 2, which is greater than 0. So I put a plus to the right of 1. And then I pick any number to the left of 1, like say 0. F double prime of 0 is 2 times 0 minus 2, which is negative. So I put a minus sign to the left of 1. So we get a lot of information from this picture. First of all, since the second derivative is positive to the right of 1, that means f is concave up on the interval from 1 to infinity, open interval. Since the second derivative is negative to the left of 1, that means f is concave down from negative infinity to 1. And additionally, since the concavity changed at 1, or since the second derivative changed signs at 1, we conclude that x equals 1 is indeed an inflection point.